Wearing white sneakers, a cowboy hat and overalls, Bernie Fowler walks into Maryland's Patuxent River every June to see how deep he can go and still see the tops of his shoes. As a young man he could see his feet on the river bottom as he stood chest deep to net blue crabs. Now in his 90s, he ventures into the river to assess the water clarity. Fowler has been collecting this data point for the past 29 years and counting, calling it sneaker depth. Scientists make precise measurements of water clarity from satellite data, but the calculations can be complex and hard to explain to people outside the discipline of oceanography. Now NASA is adopting Fowler's sneaker idea to communicate satellite measurements of water clarity, enabling the observations to be shared easily with the general public, local governments or anyone who is interested. NASA scientists calling this algorithm Fowler's sneaker depth, the depth of water, in meters, at which a person can no longer see their white shoes. The study was published in the April 2017 edition of the Optical Society journal Optics Express. Retired State Senator Fowler has been using sneaker depth as a way to communicate local changes in water clarity to his neighbors and community. Water clarity is vital because sunlight must be able to reach deep beyond the surface to help underwater plants grow and maintain a healthy ecosystem. Throughout the world, coastal waters can become murky due to excess of suspended mineral particles, for example eroded soil, or abnormally high abundances of phytoplankton, microscopic algae. While these effects occur naturally, they can be exacerbated by human activity in a watershed, such as land clearing, urban development, and the release of undertreated sewage. Poor water clarity can drastically affect human health, the food chain, and the fishing industry. Scientists sitting in an ocean ecology lab focus on accuracy, said Lachlan McKenna, an oceanographer at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and one of the study's authors. But we sometimes need better ways to communicate with the general public. Ben Crook, a 17-year-old NASA summer intern, helped derive Fowler's sneaker depth as the first author of the paper. Crook spent part of his summer analyzing Fowler's data and satellite imagery to understand local trends in water clarity. Crook and the team looked at data from the Aqua satellite's onboard instrument, the Moderate Resolution Imaging Spectroradiometer, or MODIS. The instrument measures different colors of light, or wavelengths, that are reflected from matter suspended in the water. They specifically looked at the amount of red light reflected off floating particulates and sediments that make the water appear murky. The team then developed a mathematical model to relate the amount of red light reflected, as measured by MODIS, with the sneaker depth, as physically measured by Fowler and the Patuxent River, for the years 2002 to 2016. The resulting algorithm provides an easy way to visualize and communicate water clarity to the public. It also provides satellite-observed sneaker depth measurements for any day of the year not obstructed by a lot of clouds and for the entire Patuxent River estuary. Crook and the team observed how the Patuxent's water quality varies with the season. The winter months had the largest Fowler's sneaker depth, that is best visibility, because river flow is minimal, meaning less incoming sediments, and environmental conditions are less favorable for phytoplankton growth. The late spring and early summer months tended to have the lowest sneaker depth, that is lowest visibility, because more phytoplankton and sediments are present. The study also showed potential sources that influence the Patuxent River's water clarity. In recent years, improved watershed management has reduced the impacts from land use activities that can pollute the river, such as land clearing, sewage treatment, agriculture, and urban development. Yet summer phytoplankton blooms still continue in the lower Patuxent River estuary, suggesting that the nutrients that promote blooms are coming into the river from the Chesapeake Bay, an idea that previous studies have suggested. Fowler's sneaker depth will come in as a metric to look at long-term water clarity trends for scientifically meaningful results and communicate those to the general public, said Ivona Satinik, an oceanographer with the university's Space Research Association at NASA Goddard and one of the study's authors. Satinic and the team still need to make a few refinements though. For one, they might set the maximum limit of the sneaker depth as Fowler's height, a way to retain the context of the number and honor Fowler's dedication and work on the Chesapeake Bay. Second, the team would welcome more data points from the community to help refine the algorithm. If you have a pair of old white sneakers and put them on your feet or a string and take some measurements, that could help us build a dataset and fine-tune the algorithm, said McKenna.